In this problem, we're asked to replace the loading system shown in the figure by an equivalent resultant force and specify where that resultant force's line of action intersects the member measured from A. So my approach to this problem is to replace the loading system by an equivalent resultant force and couple moment at A. And then in recognizing that this is a coplanar force system, I can then move the resultant force some distance d away from A such that that resultant force produces the same moment as the equivalent resultant moment about A. So remember what we talked about in the lecture about coplanar force systems. The moment is going to the resultant moment at A is going to be perpendicular to the resultant force. And think about your right hand rule, and therefore we can move the resultant force some distance d down the beam from A, where it will produce the same moment as the resultant moment at A. So let's start by finding the resultant force. The components of the resultant force, F sub Rx is going to equal the sum of the forces in the x direction. I'm working in, again, standard YX reference. And I'll start with the 100-pound force. It has an x component, positive x component, that is going to be equal to 100 times 3/5. And the 50-pound force has an x component that is going to be equal to plus 50 times sine 30 degrees. So F sub Rx is going to equal 85 pounds. F sub Ry be found by summing the forces in the y direction. I have the 200 pounds. I have the y component of the 100-pound force acting downward, which has a magnitude of 100 times 4/5. And the 50-pound force has a positive y component of 50 cos 30. And I do that math, and I get that F sub Ry equals 163.3 pounds. So I have the x and y components of the force resultant, so I can calculate the force resultant. I'll draw my parallelogram where this is 85 pounds, this is 163.3 pounds, and F sub r is going to be up there in that direction at some angle theta from counterclockwise from the x-axis, where F sub r equals the square root of 163.3 squared plus 85 squared, and that produces 184 pounds, and theta is the inverse tangent of 63.3 over 85, or 62.5 degrees. Okay, so we've calculated F sub r, magnitude, direction, and let's show that for now. We're going to show it at A for now. So we have F sub r is 184 pounds acting at 62.5 degrees. Okay, now let's sum the moments about A, where we will account for the movement of those three forces to point A. Let's see, I think I have enough room to do that here. So, okay, I'm a little sloppy here. So again, we found F sub r, we're going to find and F sub r is not going to change even after we move it to account for the resultant moment at A. So now we're as an intermediate step here, we're going to calculate the resultant moment about A that will account for the movement of those forces, the three forces, to point A. So the resultant moment about A, we'll assume counterclockwise is positive, is equal to the sum of the moments about A. And let me jump back down here. Equals, let's look at the 200-pound force. It is going to create a counterclockwise moment about A. So it's going to be a positive 200 times its moment arm perpendicular distance of 3 meters. I'm sorry, feet. And the 100-pound force has two components. The x component does not contribute anything to the moment since its line of action acts through A, but the y component does, and the y component is going to create a clockwise moment. So it's going to be minus its magnitude, which is 100 times 4/5 times the perpendicular distance from its line of action to A, which is 6. And then the third force has an x component. The 50-pound force has an x component that does not contribute to the moment, but its y component does, and its moment is counterclockwise about A. So we're going to add its magnitude, which is 50 times cos 30 times its perpendicular distance from A, which is 9 feet. Okay, so we do that math, and the sum of the moments, the resultant moment about A is 509.7. Let me clean that up so we're not confused here. 509.7. And that's going to be pound-feet. And it's positive, so it's acting counterclockwise. Now let's just draw that at A before we take our final step. So if we were told to find the equivalent resultant force and couple moment about A, we would be done with the problem because we have the resultant force, and here is the resultant couple moment acting counterclockwise, and it's, be consistent, we'll call it 509.7. We could round it, but okay, pound-feet. But since this is a coplanar force system, that resultant moment is perpendicular to our resultant force. And so from what we learned in the lecture, we can now move the resultant force down away from A, down the beam away from A, to a distance at which the moment that the resultant force creates about A accounts for the resultant moment about A that we just calculated. So in other words, we can put the resultant force somewhere along the beam, and let me just draw that. I know about where it's going to be, so I'm going to, and then we'll just call that distance D, but I can put it about where it's going to be. So we'll just put it out here, and note that it's still 184 pounds, and it's still acting at that 62.5 degrees. But now what we're trying to find is what distance D will result in that resultant force of 184 pounds acting at 62.5 degrees create a moment about A of 509.7 pound-feet. Okay, well, let's break the 184 pound resultant force back into its components. It had an X component of 85 pounds, okay, and it had a Y component of 163.3. Let's put those on there. 85. But note that the 85 pound X component produces no moment about A since it acts through A. So it's just the Y component of the resultant force of 184 pounds. The Y component of that 184 pound resultant force is the only component that creates a moment about A. And its moment about A is 163.3 pounds pounds acting at a distance of d, which is our unknown, and what we want to do now is set that equal to the resultant moment about A that we're trying to replace now. So we'll set that equal to 509.7, and we can calculate that the distance D needs to be 3.12 feet. Okay, so that's our final answer, and we can show that up here. D is 3.12 feet. So since this is a coplanar force system, we can express an equivalent system by just an equivalent resultant force with no equivalent resultant moment.